Anybody there?
Huh?
Is that you, Charles?
It is, maybe. Who's asking?
It's me, Michael. I was going to do another lesson.
Ooh, I like lessons. How you doing, Michael?
Yeah, I'm doing all right.
I noticed that my favorite letter is on the screen.
Yes, Charles likes the C.
Yes.
CCC, senor. Yeah, so remember we had a lesson that was triple A. So this is the triple C lesson.
That makes sense.
I don't know if it makes sense.
What about the triple B?
Triple B happened, but you have to pay premium rates to see that one.
Nice. We quadruple your tuition.
No, there's no triple B at the current time, but we can think about that for later.
Maybe for our third class.
So let's see. So we talked about game theory, and one of the cool things about game theory is it let us reason about sequential decision making and agents and learning in the context of there being more than one of them in the world.
Right.
So this is something that I wrote in my dissertation, is that in some sense MDPs are very solipsistic.
Wow. Did you actually write that?
I did. It's in my intro. Do you know the word?
Of course I do.
Okay. Do you want to define it for everybody?
No, because that actually would be ironic.
Okay, fair enough. So the idea of solipsism is that you're the only thing in the universe, and everything else is just, kind of there.
Yes.
But you're the only real thing. And so one nice thing about the game theory setting is it actually lets us admit that maybe we're not alone. So what I'd like to do in this lesson is actually dive in even more deeply to that idea and talk about how the MDP, or the Markov planning and learning type framework, can be adapted to be able to talk about coordinating between agents, communicating between agents, and actually coaching between agents.
That sounds perfect. That's actually the kind of thing that I like to do and I like to think about as part of my research. So I am looking forward to learning more.
Excellent. So the way we're going to do that is actually look at different ways that Markov models can be kind of modified and redefined so that coordination and communication and so forth is a natural property in the model. And we'll look at a couple different models. The first one is called Deckpalm DPs, and the second one is called inverse reinforcement learning, and they kind of get at these different issues in slightly different ways.
Good. I think. Well, we'll do that. We'll talk about it some more later.
Okay. To try to motivate this idea, let's look at a little example. So let's imagine we've got two agents, Agent 1 and Agent 2, and Agent 1 has a kind of a goal or some kind of reward function that it's running, and to make that reward function have high reward, Agent 1 needs an apple. Now, the apple's not far away, but it is very close to Agent 2. So what are some things that Agent 1 could do to satisfy its goal?
It could walk over to the apple.
Good. Anything else?
Well, once it gets there, it can say, I thought you were giving me an iPad, and then kick Agent 2 and run.
I see. Wrong apple. This is the food kind of apple. But you're right. Probably this particular Agent 1 would like an Apple Watch.
Yes. Well, actually, this particular Agent 1 has an Apple Watch. Then let's see. The other thing that could happen is Agent 1 could ask Agent 2 to bring him the apple.
Good. And I guess presumably Agent 1 could just do nothing and just wait for Agent 2 for the apple to just show up.
That's usually how it works.
Like, maybe Agent 2 would bring it by. I guess if maybe not apples, but like almonds. There's certainly agents that bring Agent 1 almonds.
And ice cream.
Yeah. Have you gotten ice cream in a while?
Yeah.
Okay. Then yes. Okay. That's too bad. Looks like your Apple Watch exploded. My bad.
That's okay. I'll just get another one.
Yeah, because this one's broken. Anyway, when we're doing planning or sequential decision making, we need to decide amongst these different options, if you will, or different courses of action that we could take. How do we usually do that in the frameworks that we've been talking about?
Well, if we're living in an MDP-like world, we actually define the MDP, and I think the secret sauce there is figuring out what the right rewards are. Right, and the reason I said it that way is because in the game theory case, we usually call those utilities and not rewards, and I just want to differentiate between the two of them.
Okay, and then what do we do with those?
Well, once we have rewards or utilities, we then find a policy that maximizes them. We maximize our rewards or utilities. Or actually, I guess we maximize our utilities.
It seems like we can do this sort of thing in the scenario where we've got multiple agents and they need to coordinate and communicate with each other. But it turns out it starts to get a little bit hard to define exactly what the costs are and what's the likelihood that this is actually going to work and so forth. So what we're going to do is actually think about, just like we did when we talked about Palm DPs, we said that they allow us to strike a balance between actions to gain reward and actions to gain information. And we didn't have a special other way of reasoning about that. It all ended up being folded into one model where actions are being taken and they might have informational impact and they might have reward impact. The informational impact is subservient to the reward in a sense, right? So the agent just tries to figure out, I will take an action to gain information if it helps me get more reward in the long run. And so this the Deckpalm DPs is a similar sort of idea that's going to let us put coordinating and communicating along with actions, that they become actions just like everything else. Like this ask for it becomes a kind of action, and walk to Apple becomes a kind of action. And the agents can reason about whether that's a good idea or not, depending on how to maximize their utility.
Sounds promising.
So a Deckpalm DP, I've written out the expansion of what it stands for. Decentralized, partially observable Markov decision, and then I kind of ran out of space.
Yeah, the P doesn't matter.
But you know that it's a POM DP, decentralized POM DP. And so the quantities that define the Deckpalm DP are very similar to the quantities that define a POM DP. We've got a set of states, transitions, rewards, observations, observation function. The major difference is that actions are actually taken simultaneously by a finite set of agents. There isn't just one driver. There's actually a whole, too many MCs, really not enough mics.
Well done.
There's a set of agents who actually have some say over how the transitions works. So we're going to say capital I is that finite set of agents. Actions available to an agent is A sub little I for agent I. And the transition function is a function of the joint actions taken by all the agents simultaneously. So instead of just going from a state to a next state through an action, this is actually, you could think of it as a vector with one action for each of the agents in our set.
Okay, that makes sense.
So it really is a very similar kind of quantity, but we break up where the actions are happening. They have to happen jointly. And the agents themselves, their observations about the environment are also distributed in a sense. The agent I gets to see something that's a function of the agent and the state of the world.
Mm-hmm.
All right. So this is a model. In this model, all the agents are acting cooperatively because there's one shared reward function that everybody gets. If we actually split the reward function so there's a different one for each of the agents, we get yet another model that I'm not going to talk about called a partially observable stochastic game, or POSG.
Pause.
POSG.
I'm positive that would be interesting.
Yeah. So we could pause this discussion at this point and have a side discussion.
More puns. The P stands for puns. So this makes sense and sounds great as a formalism goes, but I'm kind of I'm struck when you brought up the stochastic games thing. I was thinking the whole time, this sounds like game theory stuff.
Oh, yeah. Right, it's sort of clearly game theory when we have separate reward functions because every agent has its own personal interests. But this is, right, so the Deckpalm DP setup is a kind of common interest game, might be a word for it. The notion that there's agents acting independently, but they're all acting for the same reward.
So we could model this as game theory, or is this like some different way of thinking about it?
It's partway between game theory and POM DPs, yeah. It has elements of both. In fact, I guess it subsumes both. So you can represent any POM DP as a Deckpalm DP with just one agent, and you can represent any common interest game as a Deckpalm DP with, complete observability or maybe no states, that sort of thing. So here's some of the properties of Deckpalm DPs that are probably worth knowing about. As you pointed out, there's elements of game theory and POM DPs mixed together deliciously. And as a result, remember POM DPs, well, I told you the POM DPs were not computable. So Deckpalm DPs are also not computable. But in the finite horizon, POM DPs are p-space complete, which is probably definitely kind of hard. Deckpalm DPs are actually known to be NEXP complete, which is non-deterministic. It's like NP except with an X in the middle. Non-deterministic exponential time complete.
That sounds difficult.
Yeah, I mean, so the best that we know how to solve non-deterministic exponential time problems is double exponential time. The shortest that it could possibly be solvable is single exponential time. So it's somewhere between single and double exponential.
Oh, like 1.2 exponential.
Well, could be 1, could be 2, could be 1.8.
All right, well, as long as we have choices.
One of the beauties of this model, one of the reasons that people, in spite of this computational challenge, like to think about it, is because it, just like POM DPs are useful because they let you think about actions to gain information, Deckpalm DPs let you think about actions to communicate. An optimal solution to a Deckpalm DP has to balance the cost of communicating with the cost of not communicating. So is it worth saying this at this time?
Okay, that makes sense. That sounds like some of the other discussions about POM DPs and exploration versus exploitation trade-offs.
Right, but it gets at some of these interesting questions about communication. So this is a model that's fun to think about if you're a a multi-agent person, or even maybe a natural language person, or a natural language dialogue person, where you actually have to reason about what's worth saying.
Okay.
And there are some algorithms and heuristics that are known. There's some applications that are known. And just the last thing I want to do is run us through just a quick example, so you can have a concrete example of what it feels like to be in a Deckpalm DP.
Okay.
All right, so this should be a relatively simple example, very tiny little example, but it may be challenging. So here's what's going to happen. We are in a little 4-room museum, and we're interested in together exploring the museum. But the first thing we have to do is actually end up in the same place. So we each know which state we are in. You're in state 4, by the way.
Okay.
But you don't know which state the other person is in. You don't know where I am, for example. I know where I am, but I don't know where you are. We win if we end up in the same state. You can go basically north, south, east, west, or stay put. And and we're going to move simultaneously. If a turn ends and we're both in the same place, we win.
Okay.
So normally you would have to, issue these commands into the environment, right? You like walk around by yourself, but you need to tell me what you're going to do, so I can keep track.
Okay. And all I can do is move north, south, east, and west.
Or you can stay put.
Or I can stay put.
Yeah.
Okay.
And for what it's worth, in the Deckpalm DP model, it's a planning problem. So we can actually make up a strategy in advance, as long as we don't use it as part of the strategy what state we're starting in, because we don't know that.
Oh, so we can talk about what our strategy would be.
Yeah.
Well, I can think of sort of 3 classes of strategies.
Okay.
So one would be, one of us decides never to move. So let the other person move around.
Good.
That way we can't just miss each other, right?
Uh-huh.
And so I could not move, or you could not move.
Uh-huh.
So I was actually treating those as 2 separate things. The other one would be, we just agree on a set of actions that we will take that guarantee that we will end up in the same state.
Well, and maybe one way to do that is we'll pick a focal point. We'll pick a room that we should both go to.
Right. I was thinking 3 because 3 is my favorite number.
Oh, nice. Okay. So which of these strategies do you suppose is better? Well, it depends on exactly how rewards and discount factors are defined.
Yeah, that's true. But if we just think about cost somehow being how long it takes us to get there,
okay,
I actually guess going to the same room is probably the best one, because no matter where you are, the longest you can either take 0 steps to get there, 1 step to get there, or 2 steps to get there.
Good. Good. I think you're right, actually. So let's do that. So we decide in advance that we're going to converge on room 3, and you wake up and you find you're in room 4 to start, but I don't know that. But I know what room I'm in, and now we both get to choose an action.
Right, and I would choose the action left, assuming we aren't in the same room. I would choose the action left.
Okay. All right, and I will tell you that puts you in room 3. And I take an action that is trying to also move me towards room 3. And it worked.
Oh, we're both in room 3?
We're both in room 3.
Yay!
Hey, what do you want to see first?
Room 3.
This is the Salvador Dali room.
Oh, excellent.
All right. So this worked out actually really well for us, but you could imagine if this was a much more complicated domain, if there was a lot of stochasticity, if our task was more complicated, it might be very difficult to know what to do. For example, what if you thought you were in room 4, but you were actually in room 2, because, partial observable states being what they are. So you might not even know that you're not in room 3 yet, and it might be very difficult to get there and know that you got there.
Well, I would hope that there would be some room where we know whether we're in that room or not.
You're never sure.
Oh, I don't know. I mean, whenever you do this in a real museum, right, that's what you do. You go, look, I'll meet you at the entrance.
Well, I thought it was the Jurassic room, but it was actually the Cretaceous room.
This is why I pick the entrance or something.
Oh, I see. Yeah, like a good focal room. So like 1, like the entrance.
No, 3 was the entrance. That's why I picked it.
All right, done and done.
All right, so Deckpalm DPs give us a way to optimally trade off acting and coordinating and communicating. And I think we can now move on to the topic of coaching, so communicating and coaching. So let's imagine, instead of the scenario we talked about before, where we had an agent that himself wanted an apple and wanted to somehow use communication to help bring about a positive outcome. Let's look more particularly at this case of, okay, Agent 1 needs Agent 2 to learn a particular task, like how to fetch an apple. All right. And so what we're going to try to do is figure out how can Agent 1 convey the task to Agent 2. If Agent 2 has its own reward function, it has its own task. So we're going to try to create a task or a reward function for Agent 2 in some way that is consistent with Agent 1's goals.
Okay, so two things. One, so when you said we're going to try to create it, you mean like Agent 1 should try to create a reward function for Agent 2, right?
Yeah.
Okay.
Or to convince Agent 2 to create such a reward function on its own.
Okay, and so second, I think the first thing Agent 1 should do is not tell Agent 2 that he's trying to teach him to fetch things. I think should probably.
Yeah, fetch is not going to happen.
Right, should probably, use another nicer word. But, okay, I think I'm with you.
Yeah, that's why I said get.
Yeah, except you said fetch.
Yeah, it felt like fetch was a good word. All right. Yes. Okay. So I agree with you on that.
Okay, good. So I think I've got the task. I want to somehow get Agent 2 to get a reward function that will get it to solve some task that I want it to solve, or him.
Yeah, exactly. And so there's a bunch of different ways of thinking about this, but we're going to dive into a particular one that I think is really interesting and actually quite useful, called inverse reinforcement learning.
What? Okay.
All right, so let me set this up for you.
All right.
Okay, so what does this diagram look like to you? We've got this box in the middle labeled RL. I won't tell you what that stands for. And rewards and interaction with the environment come in, and behavior comes out.
So it looks like that.
What?
You asked me what it looked like. It looks like that. It looks like...
Yeah, but what process does that remind you of? I'll give you a hint. The
reinforcement learning.
Yeah. Okay. So that's reinforcement. Well, I want to contrast it with inverse reinforcement learning.
I see. Okay.
All right. So if this is reinforcement learning in a nutshell, then is it?
Yeah.
Okay.
Environment and rewards come in.
Yeah.
And then behavior comes out.
Right. So now I'm going to invert that. All right. So see how I changed things? I added the word inverse. I put an I in front of the RL, and I flipped these two arrows. So now in inverse reinforcement learning, the learner is experiencing the environment, and externally, from an external source, is experiencing behavior. So this is coming from those same kinds of demonstrations that you were talking about. And from that, it has to actually infer a reward function. So let's do this as an exercise.
Okay, I'm a big fan of it.
Not a quiz.
No, that would be wrong.
That would be wrong. We're in a grid world.
Okay.
And you have to learn a reward function. You have to learn what's good or not good to do in this grid, and you're going to get to learn it by watching me. So I'm going to control the agent. The agent's name is Frank.
Okay.
So he's going to go like this. And then he stays there. Okay?
Okay.
So I claim that you could actually make some very good, educated guesses about how rewards work in this environment just based on that one little demonstration.
Yeah, I think that's probably true.
So is there anything that the agent finds positively rewarding?
Green.
Green, yes. Good. Is there anything that the agent finds aversive?
So I could guess that blue is aversive because you avoided the blue, but that also happened to be one of the shortest paths to get to the green.
Yeah, that's true. That's true. So it might have just been a coincidence, but I think you have some evidence that maybe blue was something I was trying to avoid.
Right.
What about red?
So red is not something you were trying to avoid because you could have avoided it.
That's right.
I don't know about orange because you couldn't avoid orange to get to green.
Excellent. And that was exactly the inferences that I was hoping you could make. So again, you can learn a tremendous amount about what's valuable and what's not valuable by not just the path that was taken, but in a sense by the paths that were not taken and what the other options are or were and what the other options weren't. Right? So you couldn't learn anything about orange. It could be that he hates orange, not as much as he likes green. So Frank was willing to go through orange, and it didn't matter where. But red, yeah, totally could have gone around red and didn't bother, right? So that you can avoid blue and red just by going like that, but he didn't do that. So he probably is indifferent to red or something. So it's actually a really cool idea, and we can actually learn things about what people want to do and what they don't want to do. How tolerant are they of like sudden stops in a car or a bumpy road, that sort of thing. How do you trade that off against how fast you're trying to get to your destination? It's hard to get people to tell you numbers for that, but it's actually not so hard to have them demonstrate and then infer these kinds of values from their behavior. So, obviously, as we're sitting here, we can't really get into the details of the algorithm, but just to give you a kind of a hint of the form of this, there's an algorithm that I worked on called maximum likelihood inverse reinforcement learning, but there's a whole bunch of different algorithms. This one I happen to understand the best because I helped make it up. And the basic game is here, guess a reward function. In this case, we were guessing reward functions that mapped colors to values. We then compute an optimal policy with that reward function in mind, measure the probability of the data, of the behavioral trajectories that we saw given that policy, and then compute a gradient on how can the value of the rewards change in a way that would make that the data more likely. And then we just go back and do that again until we find something that is a local maximum.
Oh, that makes sense. How does that work in practice?
It seems to work pretty well. It can be slow, and it can get stuck in local minima, but we haven't really had significant problems with that. It actually pretty consistently comes up with a reward function that's pretty solid. There's tricky things like keeping in mind the fact that when I showed you the trajectory, I went through green and then I stayed there. So how do we represent that? Is this an absorbing state? And if so, do I just include it once in my trajectory, in which case it just saw one little green, in which case it's not so excited about green? Or is it really important and it kind of sat there forever, in which case it really didn't see much of anything else? So getting those terminal states right can be a bit of a trick.
That makes sense. Okay. I like that.
All right, so even though that example that we just talked about is something that I drew up on the screen, I decided I would actually turn that into a real example and ran it in Burlap with the implementation of ML IRL that's there. And this is the result. It's actually kind of neat. So here's the trajectory and the MDP that we ran in, and here's how MLIRL decided to actually assign rewards to the different colors. So you can see that the cell that's green is assigned very high positive reward. So it is drawing the agent over to that. That is a positive place to be. And you can see that the blue squares are actually fairly negative. The ones that correspond to these blue puddles are given a not insignificant negative reward, so they are actually avoided on purpose. One of the things that's interesting is, as we talked about, there's no sort of evidence in this trajectory that red is good or bad, and in fact, it ends up getting pretty much the same reward as the background, basically 0. One thing that's a little bit more interesting is that it actually concluded that this orange strip is somewhat aversive. It gave it a slightly stronger negative reward to try to get it to avoid it. And I guess that was because the demonstrated path didn't have the agent spending multiple steps there, and it could have.
Yeah.
But it didn't.
Right.
So maybe it was a bad place.
Right. So there's lots of ways that it could have gone all the way over to the orange and gone straight down.
Yep.
But since it didn't, it maybe tried to pick a path that minimized orange.
Right, and so it just kind of went with that and gave it a slightly negative reward. If we gave it a bunch more examples and we could see negative, well, whether the orange really was consistently a good thing or a bad thing, it would get fixed with more training data. But it's pretty neat how much it can pull out of actually one single example.
That's actually kind of cool, and I do like that it gets slightly negative. It doesn't believe that you're trying to avoid orange, just that. Maybe you are, because if you weren't trying to avoid orange, I guess if I thought about all the paths that could get me from where I started to where I ended up, there's a lot of them that involve touching orange more than once. And since you didn't pick that one, maybe you're trying to avoid touching orange more than once. And since they're all the same thing, that would be evidence that it's something to avoid, although it's only very slight evidence. So that turns it into slightly negative. That's kind of cool. That's kind of amazing.
Yeah, I think so too. I mean, and one of the things that I really like about this is the notion that it's actually learning not just from the positive example of where it went, but in a sense from all the different paths that it didn't take.
Right.
Right. And so the fact that it didn't hit blue, it used that as data. So it actually is combining this notion of, you're planning in the full MDP with, well, we get to see one trajectory through that. So what is that telling us about other parts of the MDP?
So I guess the short version of this is you can communicate a lot even by communicating a little. And an even shorter version of that is less is more.
Well, no, I wouldn't say that at all.
But you just did.
I did, but then I read it and I realized that that's not what you meant, or that's not what I wanted you to mean. So yes, that you can communicate a lot with a little. Less is enough. Maybe.
I like that. That's like 8 is enough. And 8 is less than 9, so less is enough. I like that.
And that pretty much sums up the 3 C's that I wanted to talk about. That sums up the different things I wanted to talk about in Triple C. So we talked about coordinating between agents, we talked about communicating between agents, and we talked about coaching, or kind of teaching, instructing between agents to convey an idea of a reward function. So what do you think? Are you ready to go through and kind of fill in the topics that we touched on in each of these?
I'm going to say No. And
I don't think that's on the script.
no, I'm going to say
You're
no.
supposed to say yes, and
No.
we're supposed to go through it.
No, and I'll tell you why. Because I think this is really cool, and I think we're giving it short shrift. I think there are several more examples that we could go through that would really kind of drive home this point, particularly the coaching and communication point. And I think we should do it. So let's do some more of these.
So what you're saying is you didn't think I lectured enough, and that I should now on the spot make up more material. That's kind of tough.
Well, I don't know. You don't have to make up more material. I mean, the material is out there. You can just very easily describe some stuff that we know about. How about doing that? No, you know.
I'd rather I'd rather not. I mean, I feel like we covered the topic, and we should just go with it.
Okay, I think I can prove to you that we haven't covered the topic, and the way I could prove it to you is simply by covering more of the topic.
Okay, that's fair.
All right, so let's do that. So you know what? Here, I'll make it easy for you. I have 2 or 3 things in mind that I think that we could talk about that would really kind of drive the point home, and I will talk about them happily.
All right, I appreciate that, and I would be very interested to hear what you have to say about these topics. So why don't we stop for now, and then you can go research those topics, and we'll come back and talk about them.
Nope, I'm ready to talk about them now.
Wow. Okay, that's impressive.
Thank you.
So you just want to take over. Okay, so the thing is, I'm actually in Rhode Island right now, and so it's not clear to me how we can just kind of switch places and let you drive.
Well, why don't we use the magic of technology?
So here's my idea, Charles. You know how in Star Trek they have a transporter room?
Yes, I do know that.
So let's see if we can do a transporter slide.
I like that. It's like the electric slide.
Yeah. All right. So I'm going to dematerialize, rematerialize someplace else, and you'll rematerialize here so you can drive the rest of the lecture.
Makes perfect sense to me. I don't see anything ridiculous about that at all. Let's do it.
Did it work?
It worked.
That's awesome.
All right. Thanks, Michael. I think it is awesome.
No, that's really cool. And you know what else?
What?
I got your almonds.
Curse you, Khan! Okay, Michael, so I wanted to, before diving into a couple of examples, I wanted to remind you of a conversation that we had earlier. Does this little picture look familiar to you?
It looks like the Monte Carlo tree search stuff we talked about in the options lesson.
It actually is. So here's the point that I wanted to make. I made the point at the time, but I wanted to really kind of drive it home here. If you recall, I asked you to come up with some options for solving Pac-Man, and you came up with 4 of them. You remember what they were?
Yeah, I think they're on the slide, fortunately. I just have to remember what they mean. It's like eat with 3 different bullets and they're getting successively larger, but I think it's actually food pellet, power pellet, monster, or ghost, and then avoid ghost.
And avoid ghost, right. And if you recall, at the time we briefly discussed that these things really do look like options. And this last one doesn't really look like an option in the sense that it doesn't have a goal and there's something you can succeed. You can, in some sense, only fail. And this turned out to be interesting for a couple of reasons. One, just because you came up with them. And in fact, we've done this study on multiple humans and of various levels of expertise. And basically, they all come up with the same 4. Sometimes they'll come up with a 5th that kind of distinguishes between eating a real ghost that's edible and a ghost that isn't edible and that kind of thing. But basically, they come up with these same 4. And the point here, and why I wanted to bring it up, is that if you just ask people to give you what they know, you ask them to communicate, you ask them to coach an agent, they will often come up with things that are different from what your machine expects. And the sort of claim I want to make is that often in research, what we do is we come up with wonderful machine learning algorithms, decide what information they need, and then try to force humans to give us that information. But actually, human beings will naturally sometimes give us that information, but often will give us different kind of information. And if you look at it the wrong way, you would say, well, look, these 3 are useful. This last one can't be implemented, so I'm going to ignore it. But in fact, even in the Monte Carlo tree search example, this last one, this constraint, actually helped us develop a better algorithm because it gave us a better rollout strategy. And in fact, as the students listening will know because they've read the paper on this that we made available, that it actually improves performance an amazing amount. So the point of this is that when we ask humans to communicate, to be a part of the sort of team of how we teach and demonstrate to our agents, we need to meet them where they are as opposed to try to force them to meet us where our algorithms are. And I want to give you just a couple of examples of that. That sound fair?
Yeah, that's really cool.
Cool. All right, so the first one's going to be something called policy shaping. And as a preview, just want you to know, the whole point of this is to say that all the stuff you talked about with reward shaping was wrong.
Oh.
Yeah. Let's take a look. Okay, Michael, so I have brought back yet another slide slightly modified from the discussion on options and constraints. Do you recognize it? You remember this?
Well, it's got the Pac-Man thing on it, and it has the 4 options or whatever that we just talked about, and it has the beginnings of a stoplight.
Right, that's exactly right. Well, so in fact, I told you a little bit about this experiment that we did where we asked people to come up with these options, but there was a second part to the experiment. There are 2 buttons. This is me attempting to draw what a button looks like. There's a green button and there's a red button. And what you're being asked to do is to watch Pac-Man over here run around, executing actions, including these options you came up with, and then occasionally you're supposed to hit a green or a red button. And what do you think that the green and the red stand for?
Probably green is the Pac-Man did something good, and the red is the Pac-Man did something not so good.
Right, that's exactly right. So this is supposed to mean good, and this is supposed to mean bad, just like you would expect. We have people do this, and they did it. They would say, that's good, that's bad, that's bad, that's bad, that's good, 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 that's bad, and so on and so forth. Now, here's my question to you. Given that people have done all of this, and they've given us lots of data on whether Pac-Man did well or did poorly, what would be kind of the obvious thing to do with that information?
The obvious thing would be, it seems like the right thing, which is to, if you treat the good as like a +1 and the bad as a -1 and have the agent just maximize reward, that should basically be reinforcement learning.
Right, and that makes a lot of sense, right? So since we do reinforcement learning, we'd want to turn this into a reinforcement learning problem, and we would say, well, every time you said something was good, I'm going to treat that as a reward of, say, 1. It doesn't really matter, and bad, say, is something like that, and you get a reward for, say, being in a state and taking a particular action. And that's a perfectly reasonable thing to do. And in fact, this ends up being a way to get human beings to help us to sort of automatically do reward shaping. And in fact, you can show this works pretty well. And there's been a lot of work on this. We provided some papers on this for the students to read about. And you do better, as you might imagine, by treating these things as reward shaping than if you didn't. Because really they're hints as you sort of move along about where you ought to be and the kinds of things you ought to do. But remember what I said before, that human beings actually are trying to tell you something, and they might be trying to tell you something different from what you want them to be. So if I think back to what you just said, what you kind of said is, well, look, it's a reinforcement learning problem. Reinforcement learning problems need rewards, and so we should convert these things into rewards. Well, it turns out that in practice, when you actually talk to humans and kind of work out what they do, they're not actually doing this. When they say good and they say bad, they're not thinking in terms of actual rewards, +1, -1, or +10 and -9 and these kinds of things, because of course they're not reinforcement learning experts. They're not thinking about rewards. They're actually giving you a different kind of information. So here, let me just ask you, if I told you in English that you should hit the green button whenever the agent does something right and the red button when the agent does something wrong, then what kind of information am I conveying other than a reward value?
Well, one way to put it is you're giving commentary on the behavior or the policy.
That's exactly right. That really, in fact, it turns out you could convert these things into rewards, but you could also convert them into something that's a bit more direct. You can just say, well, you're actually telling me that in this particular state, I should, in fact, take this action. Or that in this particular state, I should not take this action. And this is direct policy advice as opposed to reward advice. And so maybe what we're really doing is not reward shaping, or what humans are doing is not reward shaping. It's actually policy shaping.
Policy shaping.
Policy shaping.
Did you make up that word? Because I'm not sure I understand what that word means.
So I did not make up the word policy, and I did not make up the word shaping.
No, I know that. No, I'm sorry. The combination of those two words.
Well, I'm not going to say I made it up, although maybe I did. One of the papers that we're going to read is actually a paper that I was a part of the author team on, and it's all about introducing the notion of policy shaping. And it's really a very simple idea. It's sort of what I just described, that what human beings are actually doing is giving you direct policy advice, and so they're trying to shape what the policy should be directly, as opposed to trying to say something about what rewards ought to be. Does that make sense?
Yeah, I think so. I mean, I guess now before I was thinking about shaping differently, but now it's sort of feeling like sculpting to me. Like you have a policy out there and you're going to apply pressure and smoothing in different places to have it be a little bit different.
Right. So think about it this way. There's actually, I think, a direct way of doing this. When you do policy shaping, what have you actually done? What you've actually done is you've taken whatever the reward function was in, say, some particular state for some particular action, and let's say it was 0. And what you said is, no, this is the wrong answer, the wrong value. It should not be 0 here. It should actually be something else. It should be, oh, I don't know, 3. So you've actually replaced the original reward function R with another reward function R prime and said this is actually the reward function that you should be learning over. And that's really what reward shaping does for you, right? I mean, if you think back to the examples that you were giving with all the reward shaping, you were replacing reward values. Agreed?
Yeah, though in the case where we were doing potential-based shaping, we also had to make sure that whenever we sprinkled some positive reward in, there was negative reward someplace else to balance it out, so you didn't get new positive reward cycles happening.
Right, now that's true, but regardless of where you sprinkle them and what kind of constraints you put up, you still took what was originally a reward value of something like 0 and replaced it with another reward value.
I agree with that.
Plus 3, minus 3, 7, doesn't matter. So you've changed the reward function. So in exactly the same way, policy shaping is about changing the policy. There's some policy that the agent currently has, and you're saying, actually in this state, rather than whatever it was you think you should do, you should do, in fact, this. So maybe I'm confirming what you already had. Maybe I'm telling you to do something different. But regardless, I'm overriding your policy function. In the same way that in reward shaping, you're overriding the reward function.
Okay, that makes sense.
Right. So this is what policy shaping is all about. And it happens to line up with, it turns out in practice, the way people are actually trying to convey information. And so then the real question is, what do you do with this? How do I take this information that's being given, if it's not being given in the form of rewards, we know how to do that, but it's actually being given in the form of a policy, what should I actually do about it?
So I was interpreting what you described as saying, if a person gives positive feedback for an action in a state, and it's not the action that the agent would have taken in that state, then just replace it. Just make a modification of the policy so that that's the action that's taken. Is that the way to do it?
Well, ideally, that is what you would do, right? If a person tells you, look, you should go up here or you should eat a ghost here, you should just do it. But that actually requires something be true, which, as the lawyers would say, assumes facts, not an evidence. And that is that the person's actually right. What if the person's wrong?
Yeah, but certainly we should at least have that as our assumption. I mean, if we don't think the person's right, then this is a really easy thing to do policy shaping. Just ignore the person.
But what if the person's right most of the time but can occasionally be wrong?
I see.
Or what if the person's right but actually meant to say it the time step before?
I see. So maybe there's a way to use all these different things as evidence and then to combine them together to get, I don't know, kind of a best guess as to what the right answer is.
Exactly. And that's why it's policy shaping and not policy doing. So I'm going to try to give you a little quiz and see if we can kind of work out what the right thing to do is under the circumstances where a person might tell you to do something and might not always be right about it. Seem fair?
Yeah.
Okay, Michael, so here's a quiz. What's the answer?
I'm going to say 7.
That is actually correct. I don't know how you got it. All right, let me explain a little bit about what's here on the screen. So we're going to pretend you're in some particular state. Let's call it S, okay? Mm-hmm. And the agent has taken an action. And there are 3 possible actions the agent can take, X, Y, or Z. Got it? Mm-hmm. And a human being has pressed the green button or the red button. And we visited this state maybe many times and taken each of those actions maybe many, many times. And what's going to be in this table is the number of times when we've been in that state and taken a particular action that the human being has said either good, that's the right action, or bad, that's the wrong action. Now, what I'm going to ask you to do is I'm going to put some numbers in here, and then what I'm going to ask you to do is tell me what's the probability that a particular action, X, Y, or Z, is in fact the optimal action given that the human being has told you it is or is not. And the last little bit of information that you need is the probability that a human is actually correct whenever they give you a green or a red signal. Okay? Because remember, last time we set this whole thing up by pointing out that a human may not always be right.
Okay.
So for the first quiz, I'm going to tell you that the human is always with 100% one probability, absolute certainty, correct.
Okay.
And I'm going to tell you that when we've been in this state, the human has told you exactly once that X is in fact the correct action, has never told you that for Y or for Z, and has never told you whether any of the actions are incorrect. So I want you to tell me the probability that X is the optimal action, Y is the optimal action, or Z is the optimal action given the information in this table. You got it?
I think so. Can I ask some clarification questions?
If you insist.
Well, so I don't think it matters, but is there any kind of prior? We're just saying that sometimes the agent takes X, sometimes Y, sometimes Z. But other than that, the agent has no reason to believe X, Y, or Z are better. One is better than the other than this feedback that we're looking at.
Yeah, for the purposes of this discussion, yes.
And then I had another question, which is, you're saying that the person says whether such and such is a correct answer. Could it be that two of them are correct answers? Like there's two perfectly reasonable ways to act from this state. Both X and Z are fine. Is that the case, or is it exactly one is the right answer?
So that is an excellent question, Michael, and I'm going to say you tell me.
Oh, boy. If there's no prior,
Mm-hmm.
there always is a prior. So I guess it's like a uniform prior. There's no reason to think that one is more powerful than the others. All right, and then if it could be the case that multiple of these answers actually can be correct, I think we need one more piece of data if we're going to do some probability reasoning, which is not just what's the probability that the human's correct, but what's the probability that the human's going to give feedback.
Well, I'm going to claim it actually doesn't matter. When I say there's a 0 here, that means that the human doesn't have to give any feedback at all. So imagine in this case, we've been in state S exactly once, and we took action X, and the human said that was good. And that's it. And so that's why everything else is 0. Another way of putting it is whether the human, for the purposes of this, whether the human tells you an answer or not is independent of whether they've ever told you anything before and whether they'll ever tell you anything in the future.
Sure, okay, but I feel like I'd still like a probability for that. I guess what you're saying is maybe it's all going to cancel or something. I mean, there is what seems to be a really obvious answer, but I feel like you could also be setting me up for a trick, and I just want to make sure I've got all my bases covered.
Michael, have I ever tricked you? Ever?
Yes.
That is false.
I feel like you're tricking me right now.
Your paranoia is noted. Michael, I'm only about helping you to learn. So are you ready to go?
Yes.
Excellent. Then go. All right, you ready, Michael? You got an answer for me?
Sure. I have at least one answer, maybe two.
Okay.
All right. So in the case where there is only allowed to be one right answer,
yeah,
it seems pretty clear that that answer has to be X. And why is that? So the reason that is because the evidence that X is a correct answer is perfect, right? Because the person said X is the correct answer at least once, and the person's never wrong according to the little assumption in the bottom left. And so nothing else really matters. That combined with the idea that only one thing can be correct, it has to be X.
Okay, so then what would I put in the first box?
1, and then 0 and 0 for the other guys.
Right. And in fact, one way of thinking about this is that if you know there is only one optimal action, then if I tell you that X is optimal, then it's as if at the same time I actually told you that Y is not optimal and Z is not optimal.
Oh, I see. That's really useful as a general kind of rule. And that's all consistent, and it's great. And had you told me that X was said to be correct and Y was said to be correct, then I would have divided by 0 someplace and been very unhappy.
Yes, and dividing by 0 is bad.
Very bad.
All right, so you said you had maybe 2 answers. Did you just give me 3 answers, or did you mean something else?
No. Oh, sorry. Yeah, no, I have probabilities for all 3 boxes. That's one answer.
Okay.
I was trying to also think through the other case. You said that if we allow for the possibility that each of the answers, X, Y, and Z, each one independently is either right or wrong, then we have perfect information that X is correct. But that doesn't put any constraints on Y and Z. And in fact, because we got no feedback of any kind, there really isn't anything telling us to move away from our prior of whether Y is correct. Let's see, just by itself. I mean, Z could be correct or not, Y could be correct or not, and X could be correct or not. X is definitely correct. Y, we don't know anything. I mean, if you erase that sort of green one that you wrote up there.
Right. In fact, let me do that.
Oh, nicely done. That, to me, would imply that we're at our prior for Y and Z, which is a uniform prior, so half. So I want to say 1/2 a half.
Right. And we would accept either answer.
Okay.
And this makes perfect sense. Isn't that neat?
Yeah, in one case, it's like a multinomial, because all 3 of them together have to add up to 1. And in the other case, it's more like a bunch of binomials where each one individually has to be between 0 and 1.
Okay, that's a great point, Michael. Let's come back to that in a moment. I want to give you one more quiz because you like quizzes.
I do. It makes me understand whether or not I understand.
Wow. Okay, Michael, so here's the same quiz I gave you before, except now the probability that the human is correct is different. It is 0.8.
But otherwise, the feedback that we've gotten is the same?
Feedback we've gotten is the same. We've gotten one feedback-em.
And are we doing the case where exactly one answer is correct or all 3 of them can be correct?
Whichever one you want.
Let's say only one can be correct.
Sounds good to me.
All right.
In fact, I'll write that down so everyone says only one can be correct.
Ooh, that reminds me of a movie.
I don't know what you're talking about. Okay, so you ready?
Yeah, I'm going to go get a pencil. I'll be right back. But yeah, I'm ready.
Okay, while he's getting a pencil, everybody else, go. Okay, Michael, so you got an answer for me?
Yes, though it was harder than I thought, actually.
Well, you're welcome.
All right. So the question is, what's the probability that X, Y, or Z is the right answer? And I had said that I wanted to do it in the form where it's either X, Y, or Z. So this is a multinomial over X, Y, Z.
Mm-hmm.
And what we know is that the probability that the human is correct is zero point 0.8.
Yep.
And so my intuition was that it should be 0.8, 0.1, 0.1.
Okay.
Because 0.8 is the probability that the first one is correct, and then I wanted to split the probability amongst the other two because they're, we have exactly the same information about Y and Z, so they need to be the same. Then I thought, okay, well, based on the way that you were talking about it last time, it might also make sense to say that it's 0.8, 0.2, 0.2,
Mm-hmm.
which of course isn't a probability distribution, so then we need to normalize it.
Right.
And I was pretty convinced that that couldn't be right. But then I worked through the derivation using Bayes' rule, and it in fact is correct. I mean, I think what it comes down to is the same reason that the Monty Hall problem is difficult, because you have to be crystal clear on what your generative model is before you can even start talking about these kinds of probabilities.
That is excellent. In fact, I'm going to write that one down. Crystal clear and
There's an irony to the way you wrote that.
thank you. Bayes' rule and generative model. Years later, we will understand this. Right, so go ahead with that. I mean, I think this is a really important point, because when we were working this out originally, one of the problems that we had is that we kept changing what we were trying to actually compute. The probability that an action is optimal is exactly what you're trying to answer. You're not answering other questions which you might find yourself wanting to answer along the way. So go ahead, what you're saying. I'm really curious how you ended up with something.
So the generative model, I looked at a couple, but the simple one was basically, first let's imagine that the right answer is chosen, and the prior is uniform, so it's a third, a third, a third for X, Y, and Z.
Mm-hmm.
Then we imagine that we're going to be asked, is X the right answer? And we're going to give an answer.
Okay.
And that answer is either going to be yes or no.
Right.
And so what's the probability that it'll be yes or no in each of the three cases? So with a third probability, it's X, and times 4/5 probability, the answer will be yes.
Okay. And that 4/5 is because at 0.8 is the probability the human's correct, and 1/3 of the time X will actually be correct. Is that what you're telling me?
Yep, exactly.
Okay.
And then what about the Y case? The Y case is the probability that it is Y is a third,
Mm-hmm.
and the probability that the human would have said yes in the case where X was the thing that was run and Y is the actual answer is 1/5.
Yep.
And then finally, for Z, it's the same analysis, 1/3 times a fifth.
Right. And notice here that Y and Z have the same, sort of the same calculation. You don't take that and sort of distribute it around them. You got the distribution because of the 1/3 here.
Right, yeah. And if the answer really is Y, the probability that the person would have said yes to X is just a fifth. And that also goes through in the Z case.
Right.
So those actually split the probability space. Those are the exhaustive and non-overlapping cases that we need to consider. And then the last step is going to end up being just to normalize. And so we actually have the thirds all cancel, the fifths all cancel, and we have 4, 1, 1, which the information that we need, basically 4, 6, 1, 6, 1, 6, or 2/3, 1, 6, 1, 6.
Okay. Wait, where'd the 6 come from?
So once you've canceled the 5s and the 3s, you get 4, 1, 1,
Mm-hmm.
which is this is like what you call if you're trying to get information, and that adds up to 6.
6. Right.
So when we normalize, it's 4 over 6, 1 over 6, 1 over 6.
All right. So that would be 2/3, 1/6, and 1/6.
That's not a 6.
Yeah, it's a 6. For sufficiently large squiggles, that's a 6.
So that was surprising to me. That was not where I originally went. I didn't see the 2/3 popping out. Because really, like you said, where's the thirds? There's nothing in the setup of the problem that had thirds in it.
Right. And so the way that I come to that answer is I think about counting. So before, when I said, well, if I know there's only one and you tell me that that X is actually right, that's a 1. It's like also telling me that Y is not it and Z is not it. And kind of the intuition here is that if the probability of human correct is 0.8, it's almost like I'm giving 8/10 of a count. That's like saying that you got 8/10 of an X, of a count going towards X, and then 0.2 for y and 0.2 for z, which you'll notice that if you normalize that out, works out exactly to be 2/3, 1/6, and 1/6. Yeah, so that counting thing turns out to be very powerful, and we can derive a more general version of this. So this quiz is actually, both of the quizzes I gave you are actually designed to be easy. Yeah, and do you know what makes them easy? What makes them easy is that we only had one piece of data. You tried to take action X in state S, and you ended up being told that was good. But what if we had done it 10 or 20 times, and sometimes X was said to be good, sometimes said to be bad, sometimes Y was said to be good, sometimes said to be bad. Then this kind of this sort of process you went through still works, but you have to keep track of a lot more things. And this counting argument actually helps, and it comes from exactly the crystal clear generative model that uses Bayes' rule that you came up with. So I'm going to actually write it down for you, and we can talk about it for a little bit, okay?
Yeah, no, I'd like to see the general form.
Okay, Michael, so what I have here on the screen is two formulas that tell you how to compute the probability that a particular action A is the optimal one, given some evidence, which I'm calling D sub A. That is, D is the data, the set of labels, the number of the times you've said yes or no for A being the optimal action, in both the general case, where there can be any number of policies that are optimal, that is, any number of actions in a particular state, that could be optimal, versus the case where there can be only one, the Highlander case. Okay, so I'm just going to kind of read this out to you, and you can just ask me any questions you want, but we'll sort of see where it goes. So we should read the first equation in the following way. So all of these are for a particular state, and you just can apply this in every given state because we're living in Markov decision process land, and we don't have to worry about all the other states. We can just worry about the state we happen to be in. This is the probability for a given state. Action A is the optimal one given a sequence of labels that say, yes, this is optimal, no, this is not optimal, is equal to this quantity. C is just the probability the human is correct, which was 0.8 in our last quiz and was 1 in the quiz before then, raised to the power delta sub A. Now, what is delta sub A? Well, delta is just the difference between the number of times you said yes and the number of times you said no to action A. Now, what does that really mean? Well, remember, as you said when you were kind of thinking this out loud for the first one, that what we really got is multinomials and binomials. No, I mean, binomial is a special case of a multinomial. So what we really have is multinomials. So what we're really doing is flipping coins. So every time you sort of flip a coin, you're getting some evidence of whether the coin comes up heads or tails more often. And so what you have here is delta basically is a sufficient statistic that summarizes the entire sequence that you get. Now, what this means in practice is that every time I say yes and no, it's as if they cancel each other out. They drive me back towards the uniform distribution, or whatever your prior happens to be. Now, a lot of people find that difficult to wrap their heads around. It feels like if I flip a coin twice and it comes up heads once and tails once, that's evidence that it's a half. But if I flip a coin 1,000 times and 500 times it says yes and 500 times it says no, that's somehow more evidence that it's a half. And that's true, but actually in both cases, the maximum likelihood answer is still 1/2. It's just in the second case, you're even more confident about it. And what we're doing here is we're measuring basically the mean, not the variance. Does that make sense?
Yeah, I think so. Right. So it's in some sense, it's not telling us how sure we are of the answer. It's really just saying what the answer is, the best guess as to the answer.
Exactly right. And what this delta kind of summarizes for you is the only thing that matters is how many times you said yes versus how many times you said no, not how many times you said yes on its own. So in the general case, what we're really saying here is something kind of neat, which is that we can treat every single action as if they're independent. And so the probability that A is optimal depends only upon what you've told me about A. It doesn't depend upon anything else, because as we did in the first example, if you tell me that the first action is optimal, but all of them could be optimal, there's multiple optimal policies, then the fact you told me something about that action doesn't actually tell me anything about any of the other actions. And so what we have here is basically the probability that I would see that many times you've said yes, normalized by the probability I would see that many times that you would say yes, versus I would have said all those times and been wrong about it. So C to the delta A is sort of under the assumption that you are correct, and 1 minus C is under the assumption you were not correct. And that just falls out of the binomial distribution. And if we plug in our original answers, you would see that you end up with the same thing that we got before in the special case where you've only seen one label. You with me?
Yeah, that's cool. I think so. So because it's the binomial case, one per action, we're not looking at any of the other actions. So the denominator there comes from essentially the count of how likely it is that we'd have that delta number, versus that if we were wrong, we would have that delta number, the 1 minus c. So yeah, I think that feels right to me.
Now, it gets slightly more complicated in the case where there can be only one policy. And that's because, for the very reason that we described in the first quiz, where if I know with certainty there's only one policy, and I know with certainty the human gives me the right answer, the moment you tell me that some action is correct, I now know something about the other actions. So it becomes complicated. Somehow what you've told me about a second action tells me something about the first action. And when you go through all the math, it's still a multinomial. And when you go through all the math and do the derivation, and the derivation's available for the students, you end up with this quantity, that the probability that a particular action A is optimal given a sequence of labels is what we've seen before. It's C raised to the delta sub A times 1 minus C raised to all the other evidence that we have from the other actions. And then there's a normalization factor, which I don't write out here. And this corresponds to what we did in the last example where we wrote out 0.8, 0.2, and 0.2, and then normalized everything out.
And let me make sure I understand that. So we have 1.2. Oh, the delta is 1.
Yes.
No, but it's 0 for the other guys. What's delta J? Delta J is for the other actions.
Yes, this is the difference between the times you said yes and no for every other action that isn't the particular action you're asking about. So this provides evidence from the other actions.
Oh, I see. And then we're going to normalize. So
Right.
maybe that squiggle equals wants to be like an alpha, like a proportional to symbol.
Yeah, sure. I usually write squiggle, where I grew up in the South, that meant approximately. But there. That make you feel better?
Much better, because it's not really approximately, it's actually proportional to, which means we're going to have to normalize afterwards. So that we get the 0.8, we get a 0.2 and a 0.2, and then when we normalize it, we get the 2/3, 1/6, 1/6. Awesome.
Exactly. And the right thing kind of happens there. And you could write out what the normalization factor is, and then we don't have to have an alpha here. We can have an equals, but it's big, long, and hairy. And it's just much simpler to actually ignore it, do this part, which is really easy, and then do the normalization afterwards. More to the point, since what we care about is a policy, we only care about which one's maximal. We don't actually care about the actual probability.
I'm forgetting why we care about a policy.
Remember.
Because because ultimately we're combining this information to figure out what action to take.
Right.
Got it.
If all we're doing is listening to human beings, then when a human tells us something, we want to pick the action that's most likely to be optimal. And so it doesn't matter what the actual probability is so long as we have the ordering right. And so we don't have to normalize. We don't have to know the probability. We just have to make certain we get the maximal one right.
So interesting. So I'm wondering whether this, like if we have a C that is A specific, which is to say the probability that I get it right if it's one kind of thing versus the probability I get it right if it's some other kind of thing, we could probably generalize that C to having a different C for each of the actions.
Yeah, we could. I don't want to, but we could. Actually, I think the more likely case in some sense is a weird one that seems counterintuitive, which is not for every action do I have a different C, but what's the probability that I would say something is right versus the probability I would say something is wrong. Those don't have to be the same probability. This C actually represents the probability that the label I give you is correct, but there are actually more possibilities. There's a difference between a false positive and a false negative.
Got it.
So we're treating it as if there's only 2 cases here, but there's actually 4.
Okay, that's fair.
But no one wants to do it. So last thing I'll say about this before I move on to my last slide is notice that I've acted as if there's only 2 cases here. There's the case where any policy can be optimal, and then there's the case where only one can be optimal. But there's actually spaces in between here. So you could imagine a case where you might say, well, there can be more than one optimal policy, but it's more likely there's only one. It's slightly less likely that there are 2. It's slightly less likely that there are 3, and so on and so forth. And you could have a prior over any of the combinations of actions being optimal, and that prior need not be uniform. And in fact, even here, we're actually assuming a distribution over all the possible 2 to the n minus 1 policies in such a way that each action independently is equally likely. You could set things up so that, yeah, sure, it may be the case that there's more than one optimal policy, but A alone is much more likely than A and B, which is even more likely than A, B, and C, and so on and so forth.
Does that make things much hairier in terms of the formulas?
Much hairier. I mean, the reason we end up with something that's this simple over here, and this simple in the general case, and this simple in the only one case, is that we get to eliminate all the common priors.
I see.
And if we can't eliminate them, we got to carry them around with us.
Neat.
Okay, cool.
Okay, that's cool. Now, does this tell us what to do also if we have a prior that some action is correct? Because, let's say we've been learning for a while, like, yeah, that really seems like the right thing to do, and then the human is telling us something else. Can we factor in the information that we've gotten from our own experience?
That is exactly what I was going to bring up next. So why don't I do that?
Awesome.
Okay, Michael. So let me sort of jump in on that last thing that you asked me. We've just been talking about how to compute probabilities of optimal actions based upon what human beings are giving us, and that's fine. But it turns out we actually have multiple sources of information, and we would like to be able to combine them. In particular, we have some policy that we've learned that gives us a probability distribution over actions that we learned from the human. That's why it says pi sub h here. And you notice here I'm treating a policy as a probability distribution over actions. And that's all kind of neat. And these, in fact, are the numbers that we came up with in our last quiz. But while the agent is running around in the world, the agent has information from running around in the world, right? There are rewards. I've actually gone through and played Pac-Man, and I've been eaten, and I've won, and I've gone through rooms, and I've done all these kinds of things. And it seems kind of silly to ignore what I actually know about what's going on in the world, particularly in the case where a human being might, in fact, be incorrect sometimes, or may really believe that the optimal policy is one thing, but in fact, for the underlying MDP, the optimal policy is something else. So I just want to ask you a couple of really simple questions. Let's imagine that I've got some algorithm that runs around in the world on its own and learns distributions over actions in every given state, okay? And it says, after a little while, that the probability that action X is optimal is a third, action Y is optimal is a third, and action Z is being optimal is also a third. And so now I've got two sources of information. I have what the humans told me, and I know that it's 2/3, 1/6, 1/6 because math, and I've learned from experience so far that all actions are equally likely.
Which is pretty non-committal.
It is pretty non-committal. In fact, it might be what happens when you start off. If you had to choose an action in this case, which action would you choose?
X.
Why?
Oh, is that the quiz?
No, that's a question.
Oh, it's Y? Oh, wow. I had no idea why it would be Y.
Explain to me why you chose X. Sorry.
Oh, I see. Why I chose X? Because, well, according to the algorithm, it doesn't really care, doesn't have any reason to believe one over the other, but the human has reason to believe it. I guess there's one missing parameter maybe, which is how much we should believe the human. And so if we believe the human not at all, it's still not bad to go for X.
But here's the thing. We actually have that parameter because
that was C.
And in fact, it doesn't matter what C is because that's all inside this distribution. This distribution, 2/3, 1/6, 1/6, actually already incorporates all the information about the uncertainty of the human.
I don't think it does.
Yeah, absolutely does. The probability that X is optimal is, in fact, a function of the data that the human has given us and how likely they are to be correct in the data that they've given us.
But it seems like it could change over time as we've come to believe the algorithm more. Then we should believe the human less.
It's really interesting you say that because all the other the various techniques that have been out there in the world actually do that. They actually try to capture what the human has said and what you've learned in the world, and then over time believe the human less and less often because whatever the real world is telling you has got to be correct. What's actually beautiful about this particular mechanism that we described in the last couple of slides is that parameter C, that confidence that we have, that probability that the human is correct, actually sort of captures everything we need to know. If we are completely certain about the human, then these numbers will reflect that by peaking over whatever action should be optimal. And if we're uncertain about the human, then these things will tend to stay towards the uniform. Let's imagine, for example, that there is truly only one optimal action. Then, as we spend an infinite amount of time running around in the world, our notion of which action is optimal over here, if we can convert them into actual probabilities, will drive whatever the optimal action is towards one. And that just comes from all the stuff we've been talking about with reinforcement learning for all the time in this class. If we can get to an optimal policy by just experiencing things in the world, then eventually these numbers will reflect that. And it doesn't matter what the human thinks. the real world will drive the correct answer towards 1.
So you're saying that C doesn't change over time?
C could change over time, but let's just imagine it doesn't. Let's just say it's we pick a value for C and it comes out this way. If you want to say that C changes over time, that's okay, but then we're going to deal with that question by having these numbers here reflect whatever we think C happens to be. Remember, we can keep track of all the labels that we've seen, and for any given value of C that we have, we can just change these numbers appropriately.
Okay.
So it sort of doesn't matter. At the time we asked this question, I've got a distribution of actions according to the human. I've got a distribution of actions according to my experience in the world. It no longer matters what I think about the human because that is captured by this distribution. So I can just ask the question, what should I do? And here you think the answer is X.
Yeah.
Now, what if I had different numbers here?
Then I still think it's X.
Oh, yeah? What if it's this?
Well, now I can certainly justify Y.
Why?
Yeah.
Tell me why you think Y.
So, okay, so are we supposed to imagine that the pi sub A is, like, can the algorithm be wrong?
The algorithm could be wrong, but in the same way that we don't have to worry about what's wrong with the human because the distribution captures it, let's make the same assumption here. The agent, well, this distribution is going to capture all of our uncertainty about the agent's beliefs. So maybe we'll never actually see 0, 1, 0, but we'll see numbers that are close enough that I'm just going to write out 0, 1, 0.
Boy, there's a lot of ways to combine these numbers together in which Y ends up being the winner. But it strikes me that in particular, if we believe pi sub A, then pi sub A is absolutely certain that it's Y. So it almost doesn't matter at this point what pi sub H thinks, what the human thinks.
Mm-hmm. And by the way, by the same argument, if it's the case that C is equal to 1 for the human, that the human is infallible, then it really is not going to matter what the agent thinks because the human's infallible.
Well, but unless they disagree, but then we have to really believe that probability is correct.
Right. Either the probability is correct or it's incorrect. And for the purposes of answering this question, let's just say the probabilities are correct. Insofar as they are not, it'll be reflected by these distributions.
So we could never have 1, 0, 0 on the top row and then 0, 1, 0 on the bottom row because that just violates the laws of reality.
Right. So you would argue for Y.
I would.
I think that you've been using intuition so far, and I want you to do a little bit more than intuition, so I'm going to do that by writing out a quiz. So, Michael, here's the quiz. What we have here is a probability distribution from the human over optimality for each action, X, Y, and Z, and we have a similar distribution for each action from the agent for X, Y, and Z. And I want you to look at these numbers and tell me which action I should actually choose given these numbers. Should I choose action X? Here's a radio button for it. Action Y, here's a radio button for it. Or action Z, here's a radio button for it. Got it? You understand the quiz?
I hope so.
Excellent. So then, do you have any other questions? The answer is no, by the way.
No, by the way.
Excellent. Then go. Okay, Michael, you got an answer?
I do. I don't feel very solid about it, but I do have an answer.
Okay, what's the answer?
So the human thinks X, and the algorithm thinks Z, and the algorithm's more sure, so Z.
Mm-hmm. Ah, but the human's also pretty sure Z's not it.
Yeah, but it's not as... Oh, so you think Y? Or could it be Y? No, because it's just as unsure.
Okay, so you think the answer is Z, and by the way, yes. So I'll help you in your derivation by telling you that that is in fact correct.
Sure. Okay, that helps to some degree.
Yeah, it's much easier to prove things if you know they're true.
That's not necessarily true.
No, I think it's a well-established fact that if you know something is true, it's easier to arrive than if you're not sure whether it's true.
So the point is, if I want to try to be systematic about this, I need some kind of generative model again. And
yes,
I could imagine two different generative models. So one generative model says, here's what we do. There is the right answer. The way we're going to pick the right answer is by first picking who's going to get to decide the right answer, the human or the agent, and they're both correct, so we do 50-50 on those. Then we choose, according to the agent's probability, what the right answer is, and then we see if we're right. So what that would do in terms of setting up all these probabilities is we average the two different X numbers, the two different Y numbers, and the two different Z numbers, and I want to say and then normalize, but I don't think we need to at that point. I think they'll already be set up to sum to 1. Another way to think about it is that essentially what's happening is they're both H and A, both the human and the algorithm are just correct. They're choosing things according to those probabilities. And reality adds the constraint that they have to agree because there's just one right answer.
Mm-hmm.
So then we could say, well, what's the probability that both of them choose X, or both of them choose Y, or both of them choose Z?
Mm-hmm.
And that's the pairwise product of the two x numbers, the two y numbers, and the two z numbers normalized.
Right. So, and in fact, that is in general the way that you combine multiple sources of information when they are represented as probability distributions under exactly the assumptions that you mentioned. The fact that there's a human being involved and there's an agent involved is neither here nor there. If you've got two probability distributions, let's call it 1 and 2, and they are estimated from samples, and in some ways the human being was estimating from samples, we don't know what they are, but this distribution reflects that, and the other one's estimated from samples. If you want to know what the maximum likelihood action is, the maximum likelihood coin flip, however you want to think about it, you basically just take their products. So the action that I should choose is simply the one that maximizes this expression, the one that maximizes the probability that A, or that particular action, is the optimal one given what pi 1 says and what pi 2 says. And in fact, what this exactly captures is the probability that they will agree. All right, Michael, last example I want to give you is something that comes from the world of what's called drama management. And the way I'm going to introduce this to you is I'm going to point out what we've actually been talking about so far. So I'm cheating a little bit for you and helping you with what have we learned part of the lesson. So I'm going to claim that if you think about at least the last few things about communication and coaching, particularly on the coaching thing with human beings, we've kind of talked about three different ways that a human can communicate to an agent. The first is demonstrations, right? You showed the example of one particular drawing through a grid world to do inverse reinforcement learning, and that was a demonstration. And I can give you multiple demonstrations. We talked a little bit about rewards, and that what a human can give you is rewards for various things that you do, and that's a kind of reward shaping way. And the last thing we talked about was policy shaping, where what the human is communicating to you is not demonstrations and not reward values, but actually telling you what the correct policy thing is in response to things that you've done. And the last policies is different from the first demonstrations in that in the first case, you would actually demonstrate what the right action is. But here with the policy shaping, you're just giving critique that gives information about whether a particular policy is correct or not. Does that make sense?
Yeah, that's interesting. There's these different kind of mechanisms for giving feedback.
Right. So I want to talk about another sort of model and way of doing coordination, this time between a human and an agent who's interacting with another human, right? So in the cases we described before, there were two. There was, the human and there was an agent. But here I'm going to say there's a third person. So I'm going to replace the human with what I'm going to call a player. For example, a player of a game like Pac-Man. The agent, which in this case would be Pac-Man. And a third human, I'm going to call the author. So in the world of drama management, there's this basic idea that there are these things like choose your own adventure stories. There's ways of seeing tasks in the world as if they are games, where there's some author, someone who designs the game, designs the system, whether it be Pac-Man or a story or a movie or anything that you can imagine, any sort of interaction in the world, and wants to build an agent which is actually a system which interferes with a third agent, so to speak, which is the player, the person that's controlling what's going on in this world. So in this Pac-Man example, the author would be the person that created Pac-Man. The player would be the person controlling Pac-Man, running around in this world and eating. And then the agent would be the actual Pac-Man game itself. And that agent might have the ability to change the way the ghosts behave, to set up another level that has different properties, or whatever it wants. And the goal of the agent is to create an experience for the player that is consistent with whatever it is the author wants. Does that make any sense at all?
At a high level, how does the author express what he or she wants?
That's a good point. So the author wants to tell the agent something, the player is going to be interacting with the agent, and the author never gets to play with the player. How does the author express to the agent what it wants? Well, that's what I'm going to talk about, but let me just kind of give you a little preview. Imagine that the author says to the agent, I want the player to be able to win every level, but only after they've died several times in that level. I want the player to feel like they have to learn how to play better. So the game has to be hard, but it can't be so hard that the player can never win.
Okay.
Now, I haven't told you how to communicate that with numbers, but you can imagine that that's an objective function. It's a thing I could write down that I keep track of, how quickly A player can go through a level, whether it gets better over time. I could come up with a function that tries to capture elements of that, either directly through the experience or by describing properties of the game, properties of the Pac-Man level that need to be traded off one another in terms of things like difficulty.
Good.
So there's lots of ways of doing it, and people have been worrying about this problem for many, many years now. And I want to describe a particular mechanism that combines this notion of demonstrations and rewards so that you can come up with a way for this author to convey information to the agent so that the player has an experience that is consistent with the author's intent. Okay?
Neat. Yeah, that seems to fit with a couple of the things we've been talking about in this lesson.
Excellent. So let's dive in. Okay, Michael. So I think I have basically one more thing that I want to say before I start writing out little formulas and trying to convince you that this is something that we can do with some of the framework and infrastructure that we built so far. And I want to do it by diving in and sort of doubling down on this idea of drama management, on this idea of going through a story. So you're an AI person, and you need to kind of think about how you're going to build a system where a player can learn how to go through a story or can go through a story and have a good time. So the first question I'm going to claim you're going to have to ask yourself is, well, what's a story? What's a story really? And for the purposes of this discussion, I'm going to just assert something, and you can tell me if it makes sense to you, and that is that a story, it turns out, is just a trajectory. It's just one of many number of possible trajectories through a space that is made up of plot points. So does that make any sense to you? Do you know what I mean by that?
So you're being abstract about what stories are.
Yes, I'm being very abstract. That abstraction is important because we're computationalists.
And plot points, I guess plot points makes me picture a graph where there's points and there's edges, or there's vertices and there's edges. So plot point is like a vertex?
Yes, right. So a plot point is like a little circle, and that plot point might represent something like, I don't know, what's your favorite kind of story?
Mystery.
You like mysteries. Okay, cool. So I have a plot point that's something that has to do with the mystery. So what happens in a mystery? So there's a murder.
What?
Yes, that's a plot point. There's another plot point maybe, and that plot point is there's an accusation. There's another plot point, which is a weapon is found. And there's a whole bunch of these, and if they're set up right and they're sequenced just right, if of all the possible paths through all the possible plot points are set up just right, so you see the murder, you see the accusation, a weapon is found, and so on, then you have something that looks like a murder mystery. Now, I want to point out that it's possible to have good murder mysteries and bad murder mysteries. So if you think about the way a murder mystery works, right, it's got this really neat structure. There's a murder. Nobody knows who did it. That's what makes it a mystery. And then eventually you discover that every single person in the house had a reason to kill the person who was killed. And you find a weapon that points to a particular person. It's Michael. Everyone knows it's that person. And then that person gets killed. That's Michael again.
Oh, no.
And then therefore, it wasn't Michael.
Or Curly.
And so then you keep going, and you discover it was, in fact, not Curly. And then you find out who the real murderer is, and there's a whole bunch of things that happen very quickly, and it turns out it was the butler all along.
That would have been my guess.
And that makes it a good murder mystery. Now, here's a bad murder mystery. There's a murder, and you happen to see it, and so you know who the murderer is.
Okay.
And so then the murderer has to go off and start killing you and everyone else they can. You run away, and you know what you've got instead?
Chasing movie.
You've got a horror movie. So the difference between a murder mystery and a horror movie, there's not that much difference. It's really about whether you know who's doing the killing or not. So if I have all these elements lined up in some kind of, I don't know, virtual game, depending upon what the player of the game is doing, I may have to interact with what's actually going on underneath so that the player experiences a murder mystery as opposed to experiencing a horror flick.
And when you say you might have to do that, you mean the drama manager.
Right, because the agent can describe what it means to be a murder mystery, and as a player, the author can't control the player. As the player is going through, the system may have to interact with that in order to make certain that you still get a good murder mystery as opposed to something else. And I'm going to claim that if we think of these points as being key things that happen in the story, and some sequences are better than others, then what we end up with is a story is a trajectory. It's a trajectory through these plot points, and that a good story is a particular kind of trajectory, and there are bad stories, which are other kinds of trajectories, and we need to figure out how to influence the player in such a way that we go down the good trajectories instead of the bad trajectories.
And can you say a word about what the player's doing here?
Well, so it would depend upon the situation, but imagine that, you've played games like Zork, and
Sure.
various other things, right? You have vague memories of Hitchhiker's Guide to the Galaxy and those like text adventure games. You're interacting with the system somehow, and you decide to go north, or you decide to open a door, or you decide to talk to somebody. It's just like a choose your own adventure story. That's the kind of idea that I'm trying to evoke here.
Interesting. Okay. And so you're saying that we could think of this as a kind of MDP and then do reinforcement learning in it?
Yes, that's what I'm going to talk about. I want to convince you, if you buy this idea of story as trajectory with plot points, then it's actually pretty easy to turn it into an MDP.
Okay. I would like to hear about that.
Okay, let's do that. So we can take all of that and just turn it into an MDP, and I think it's pretty straightforward to think how you turn this kind of story management system into a Markov decision process, right? So what are states? Well, we said that last time. States are just partial trajectories or partial plot sequences. Actions, well, they're the story actions that the system can take. Your model is still the same model that we're using before, except it's a player model. That means, we've seen a sequence of states, or we've seen these trajectories. Some action is being taken, and I want to know what plot state we're likely to be in, given that the player is doing something. So it still looks just like a transition model. And then the rewards mean exactly what they meant before, except here they're actually standing in for some notion of what some writer of a story thinks of as a good story.
And you can somehow formalize that so that you can plan?
Yeah, well, you could, but that gets us to a whole nother discussion about where rewards come from, which is probably a discussion that we should have someday. So maybe we'll do that towards the end of the class. But just imagine that right now you have the reward function the same way that you would with any other MDP, and you don't really worry about where it comes from. It's just there.
Okay, and given that these trajectories, that the states are now these full trajectories, it seems like that makes some things harder because now there could be a lot of them. But on the other hand, you can never go back to a state you've been in before, so it's acyclic, right? So you can actually solve it more efficiently because you don't have to run, basically one value iteration and you're done.
Well, that's actually kind of neat that you said that. So, because I was about to say that there are two problems with this. The first problem is, well, now that you don't have states, but you have sequences of states, that's a lot of new states. How big do you think that is?
I'm going to say very.
It is very, very big. In fact, we can be even more quantitative than that. It's actually hyper exponential. It's like 2 to the 2 to the n.
Where, in terms of the length of the sequence?
Yes, of all possible sequences you can have, the number of states.
Okay. Yes. Okay. All right.
Right, because the number of states is sort of in factorial and all the different kind of that we can have, but all the states don't have to actually be there. And so at the end of the day, it ends up looking something like 2 to the 2 to the n. It can be really, really, really big. So the space that we're looking over of all possible trajectories where things might be there, things might not be there, gets really, really big very quickly. So that's one point that you said. But on the other hand, it turns out that there's structure there that we're going to be able to take advantage of. And in fact, that's what we do and why we're bothering to introduce this formalism that I mentioned earlier. So let's do that. Actually, before we do that, let me mention one other problem with thinking about things as Markov decision processes. And it's going to be a problem with the strength of a Markov decision process. So what is the goal of reinforcement learning? What's the goal of solving an MDP?
Maximize reward.
You maximize reward. So in fact, it turns out that if you take this sort of notion of storytelling and how I can get someone to do a choose your own adventure, and I've got rewards, I've got some evaluation of what best stories are, what's going to happen? What is the system going to learn how to do?
Make the author happy?
Make the author happy. That's exactly right, but not necessarily make the player happy. So what ends up happening with Markov decision processes, using sort of modeling this as Markov decision processes in the obvious way, is that you force the player to experience the best story. No matter what the player does, no matter how it tries, whatever choices you're trying to make, nope. The system is going to make certain that you're going to enjoy yourself, damn it. And enjoying yourself means whatever the author thinks enjoying yourself means.
So like grad school.
It's just like grad school.
No. That's not right. So are you saying that the problem, why is that a problem? Because the author, in a book, that is certainly what happens. The author gets to choose what you're going to experience.
And that's a good argument. But if we're bothering with this whole kind of interactive entertainment, choose your own adventure story, then if you don't really have any choice in what you do, then it's not really a choose your own adventure story.
Got it.
The basic idea here is because there is a reward and because all the algorithms we've ever thought about with Markov decision processes are about maximizing long-term reward, that is finding an answer. It's going to find an answer is going to force you down a particular path. But it turns out we can relax that need to find the best answer and actually end up solving the hyperexponential problem at the same time. So let's do that. So in order to deal with those problems, we're going to introduce an extension to Markov decision processes called TDD MDPs, as opposed to plain old MDPs.
TTD MDPs.
TTD MDPs, because it rolls off the tongue.
What does it mean?
Well, it means targeted trajectory distribution.
Oh.
Obviously. And that actually, you can see that when you think about how we go from an MDP to a TDD MDP. So what we try to do here is we want to make explicit those things that we said before. So instead of having states, we now have trajectories. And that's just all partial plot sequences that we can have, that we can reach, that we can get to. So it's the sequence so far. It's the story so far. I try to go back and forth between trajectories and sequences as opposed to stories because this is actually more general than the story example that we're using. Actions are exactly the same as they were before. We have a model, but now because we have trajectories instead of states, we have a model that says, well, if I'm in a trajectory and I take a particular action, what's the next trajectory that I will see? But it's still basically the same thing, except it elevates this notion of trajectories to sort of to a first-class citizen, and that we're reasoning over trajectories now. And now instead of having a simple reward, we have a target distribution. Now here I've made a sort of capital T instead of a lowercase t, and that's because the lowercase t here was sort of standing for trajectories. The capital T stands for final trajectories.
Uh-oh.
That is, ends of stories. So you don't have a distribution, or I guess you could say have a probability of 0 for all partial distributions, but all what you really care about is stories that we care about. So things that have higher probability are stories that you might consider good, and things that have lower probability, stories that you might consider bad or less desirable. Does that make sense?
I guess so, but why not just pick the one that we want and just and call that? I guess the distribution where the right story has probability of 1 and everything else is 0 seems to make sense.
Right, so that's a sort of strict generalization of what we were talking about. This is a strict generalization of what we were talking about before. So this allows us to say some things are better than others, and it turns out by relaxing this hard constraint that I'm trying to maximize reward, but instead I'm trying to match a distribution. It allows more replayability, it allows players to do a few more things, because now our goal is not to find a policy that maps states to actions in order to maximize long-term reward. It's to find a probabilistic policy. That is, a probability distribution over actions. Okay? And what is the optimal policy? It's the one that, if I use this probability distribution, would lead to be matching the target distribution.
I see.
Right?
Now, and so that I'm still on board here, the actions here are the things that the story can do,
right? The story or the story manager or the system can do,
and the uncertainty for that thing. The uncertainty is, well, what is the player actually going to do? We don't know.
Right.
Okay, so it's not the player's actions; it's the story's actions.
Right. Right. Exactly. It's story actions or system actions or manager actions. There are lots of ways to sort of think about
things like we're going to make a wolf appear right about now.
Yes, exactly. That was me doing a wolf.
Oh, shoot. I was really scared.
Or I'm going to make a key appear. Or I'm going to unlock a door. I'm going to lock a door because I don't want you to go in this room.
Got it.
Right. So these are the kind of actions that you might be able to take in the system. The model says, well, if I'm in some trajectory and I take one of these story actions, what plot point will I end up in next? What trajectory will I see next? That depends upon the player. And so all of your uncertainty here sort of probably comes from the player. That's where all your entropy comes from.
Okay.
And I'm trying to get some stories, and some stories I want to happen more often than others, but this allows the player agency by doing this sort of probability distribution. Now, there's a lot of math that I could do here, but at the end of the day, what you might think is that, well, now that I no longer have this sort of simple constraint of maximizing my long-term expected reward, but I have probabilities and randomness and probabilistic policies, this is going to be harder, much harder to deal with.
Oh.
But it turns out it's not. This is often the case in machine learning and AI. If you relax a hard constraint and make it a soft constraint, you make it something that's more about probabilities and probabilistic sort of search, you actually get more power out of it, and you're able to solve hard problems. So without going into the details, I can point you to a paper that you can, or actually a series of papers that you can read here. It turns out that by going from a hard constraint to probability distributions, you can actually solve a TDD MDP in linear time.
Linear in what?
Linear in the length of a story.
That seems unlikely.
Well, I can prove it to you, but instead what I'm doing is have you read the paper. All of this kind of induces a tree, right? You start in some state, There's several actions you could take, which gets you to another set of states, and so on and so forth. And this tree really kind of builds up. And you have a whole bunch, in fact, a hyper exponential number of possible stories. Well, if I have a probability distribution for all partial trajectories, then it turns out that whatever state I happen to be in right now, let's say this one, I don't actually have to care about any of the rest of the tree. It doesn't matter because I can't get there. See, as you pointed out, it's acyclical. So even though I can get from one plot point to another, I can't see a sequence that doesn't involve going this way.
Sure,
Does
but
that
there's
make
still,
sense?
yeah, that's right. But underneath that node, there's still an awful lot of other nodes.
But if I have a probability distribution for all of the next states I could get to, then I simply have to execute the action, and then I will end up in one of these states. And when I do, it doesn't matter what the other ones were. And so all that's ever happening is that I am following one particular path down the tree.
And how do we get from that target distribution that's kind of specifies the goal to a target distribution over all the intermediate nodes of the tree?
Right. That's the hard part.
Okay.
But it turns out there are easy answers to it.
Okay.
I'm just not going to tell you what they are.
Cool. And have you used this for actually making stories?
Yeah, we actually have done this for making stories, and actually shown that you can get people to feel satisfied in the stories or experiences that they're having, and you can do it in real time on the fly. And I'll just leave you with this little teaser. It involves using Koblik-Leibler divergence.
That's not exactly the most exciting teaser. I thought you were going to say something about wolves again.
Well, in the end, that's all a wolf is. I would love to talk about it, but I think, it's probably beyond the scope of the class. But we'll put in the resources link a series of papers that talk about this. But the real answer is that anytime you're trying to match probability distributions, you care about Kale divergence. And Kale divergence is just a bunch of sums of probabilities. And sums mean linear independence. Independence means I can do them in any order. So I can basically just ignore all the things that I don't actually see, and I only ever see a finite, and not just finite, but linear in the number of plot points at any given time. And the hard part, as you recognize, is figuring out what probability distributions are for the intermediate nodes. And that can be very hard because it can require computing the whole hyperexponential tree, or it can be very easy if you have a nice function that can map partial trajectories into probabilities or some other kind of value.
Cool.
Okay, Michael, so with that, I think we're kind of done with this lesson. Those are the three things that I wanted to mention. And I think we can now go back to where you left off and talk about what we have learned. Except I have the pen, and so you have to tell me what we've learned. I don't have to tell you.
This is true. So now when you say the three things, what were the three things that you talked about?
Oh, you're trying to trick me into telling me what we've learned.
Yeah, a little bit. All right. So when I had the pen, we talked about two main things. Well, the overall topic is this CCC,
Right.
which is Comedy Central committees.
No.
Closed caption clowns.
No.
So coordinating, communicating, and coaching.
Right.
Ha!
I think what we learned is that alliteration can be fun.
Yeah, well, sure. And in particular, I talked about two particular models. One was the Deckpalm DP model, which at least let us define or ask questions about what it means to coordinate and communicate optimally when we've got agents that don't share a brain, but they do share a reward function. So what's good for each one of them is good for the community.
Right. Shared R, distinct brains. I like that.
Then we talked about the inverse reinforcement learning idea, which was that we could actually use examples of behavior or demonstrations of behavior to infer reward functions. And then once we have those reward functions, we could try to optimize them in other settings.
Yep. We go from behaviors to rewards instead of going from rewards to behavior. And that is what makes it inverse.
And having those rewards means that it generalizes to other settings as well.
Right. And I think that a point that I made on that when I started taking over the pen was that this actually is a kind of reward shaping by getting human beings to give us hints about what we ought to be doing.
Okay, but in the form of behavior demonstrations.
But in the form of behavior demonstration. Oh, and that is a nice little point worth making, which is demonstrations are one way to do coaching. What were the other ways we did some coaching?
So, Yeah, demonstrations is one we do too. Oh, and then there was this kind of policy feedback or policy, I guess you called it policy shaping.
Right.
But it was this sort of idea that you can give feedback on the actions being taken by the agent, and that can be incorporated or combined with other suggestions as well as what the learner is picking up on its own.
And so between reward shaping, demonstrations, and policy shaping, we got a nice little set of ways that human beings can communicate to agents. So let's see. I know I did more than this. There were some examples that I used. What kind of examples did I use?
Well, in the policy shaping setting, we talked about Pac-Man.
Yeah. So we learned that Pac-Man is like the one example you should use for everything.
Sure, except for what we did at the end, which was drama management.
Right. Right. We talked about drama management, and in particular, we introduced TDD MDPs.
Where TTD MDP has something to do with trajectories and drama.
Targets and stuff. That's exactly right. And I think we had a nice little conversation here tying some of these things back to things we did before. We actually returned and brought up again constraints and options as a way of doing coaching and communication, and try to really drive home the point that, there's some human beings and they think a particular way, and then there are machines and they think a particular way, and we should try to move the machines closer to the humans rather than forcing the humans to come all the way over to the machines.
Yeah, I like that as a philosophy.
And that's really what I think is important. Yeah, that's a good philosophy. Well, I think that covers everything, Michael.
Nice.
I feel pretty good about that. Nice. So does this mean we're done? I think this means we're done with the class, kind of.
Oh, really? So maybe we should do some kind of wrap up to see how everything ties together.
Yeah, let's do that. That way I don't have to say goodbye. Why don't you come down to Atlanta, and maybe we can record some stuff together.
Great. I will have done that.
Perfect. Or is that perfect, or is that the past perfect, pluperfect?
Pluperfect.
Yeah, it's the pluperfect. Good, pluperfect. Okay, Michael. Well, I will see you in Atlanta soon.
Bye, Charles.
Bye.